All right, are we live? Hello? 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 Welcome, welcome. Guten Abend. Guten Abend. So, we are here today to continue working on these interview questions. Yeah, I'd like to just kind of take a moment before I start to just say hi. So, hello. Welcome. Let's get into it. Let's get into it. Started exercising again. I started showering each day, and I realized a couple things. My hands were bleeding because here's the problem, by the way. I haven't looked at it yet. Doing it fresh out the gate. Out the gate. My hands were bleeding because of the dry air during the winter, and I didn't realize that I wash my hands a lot. My dad taught me when I was a kid to every time you go inside, wash your hands. Every time you get your hands dirty, wash your hands. Constantly keep your hands clean because you can get sick, right, from the pathogens on your hands. Pathogens. And when you wash your hands with soap, there's oil on the top of your skin that your skin produces to protect itself. It has like kind of a protective layer. When you wash your hands with soap, especially strong soap, it actually removes that protective layer. And because you remove that layer, your skin is now more exposed and weaker to the air. And so my hands started bleeding because I had no protection on my hands. The natural protection was washed away. And so they were bleeding. I mean, bleeding, not they weren't just cut and cracked. They were actually bloody. And now that they're starting to heal because I just stopped washing my hands. Sounds kind of gross, but actually what I do wash my hands depending on what it is. If it's something where I think my hands are really dirty and I should wash them, then I'll do it. But oh yeah, if you go to the bathroom, right, wash your hands. If you come inside, wash your hands. If you do anything, get your hands dirty, wash your hands. When you're in the shower, make sure you wash your hands first because you're gonna wash your body with your hands. But I decided to start only washing the front side of my hands. For some reason, that seems to have a different kind of structure, the skin, so it's not it doesn't bleed on this side. It's not hurt, not painful, which is amazing. I mean, praise God, thank God for His creation. But yeah, don't want to mess around with your body too much. You don't want to screw around with your body, what God did. And the same thing with my hair. I think one of the reasons my hair is starting to fall out. I have a receding hairline, and so I'm starting to really notice it and starting to get kind of sad looking at it. So I'm getting older, but I don't think I'm getting that much older. Like, it's just kind of happening. And I think the reason is because I use so much soap when I wash my hair. And the same thing, like your skin bleeding, right? It removes all the natural protection, and then now your hair is, not as healthy as it should be. So if you just wash it with water and then wash it with soap whenever it's appropriate. I mean, even with just water, I mean, it's still, I could feel it. It's pretty, like, it's dried out, like it definitely, it's a different texture, I guess. All those healthy natural oils in your hair is good. And it's sad too, is when I was a kid, a girl made fun of me when I was in middle school. And she was like, oh, your hair is oily. Ew, right? I liked her too. I was like, oh, it's a cute girl. And I wasn't like into her or anything. I wasn't crazy about her, but I liked her. And she just like out the gate made fun of my hair, and I was like, don't talk to me. Leave me alone. I actually, the problem was, like, I didn't understand what she meant. I was like, what do you mean my hair is oily? She's like, it's oily. I was like, I don't know what you mean. It's like, and, from there on, I was like, I don't think I'm gonna get along with this person. Already doesn't like me because of my hair, and I don't understand what she means. I don't understand what I learned later in life, that when a girl says you have oily hair, what she means is that your hair is dirty. And she thinks you should take a shower. So now I'm very keen to keep my hair not oily, but I also noticed, like, my hair looks a lot better when it's oily because it's healthier. Like, it looks so much better. Like, my hair looks kind of like, I know it's kind of girly thing, like, oh, your hair, but no, I don't know. I mean, I think I look like a little boy after I take a shower, like, because my hair just looks so not right. And I'm like, maybe I should have more oil in my hair. I think I like it. I like it. I think I look better. Look more like a man. Look more like a man. But anyway, certain irony there though, where it's like talking about something that's traditionally feminine, your looks, with regard to wanting to look more masculine. I don't know, man. There's a lot to like the look and feel of things. Psychosomatic kind of how things look and feel matters. Matters. Anyway, back to the problem. Back to the problem at hand. You are playing the following flip game with your friend. Given a string that contains only these two characters, plus and minus, you and your friend take turns to flip two consecutive plus plus into minus minus. The game ends when a person can no longer make a move, and therefore the other person will be the winner. Write a function to determine if the starting player can guarantee a win. True. Starting player can guarantee a win by flipping the middle to become flip the middle, and so they can't make a move. Derive your algorithm's runtime complexity. Whoa. Oh wow. Okay, that's okay. This is a challenging question here. I've solved similar problems like this in the past, but I spent a lot of time on problems like this in the past. Something like this, I think it would take me a while out the gate, but well, basically, there's let's go with the brute force approach, right? So for starters, I probably don't want to use a string. I probably want to use a vector of characters, so that way I can easily modify each character as we go, so to maintain state. And I probably want to use like a depth first search type of algorithm. The thing here that's tricky is you have a series of different moves, and then the other player has a series of moves, and pretty much what you want to do. I mean, one approach like this is, I guess, probably the approach I'm going to go with, but the sort of what do they call that? The brute force approach is, you basically depth first search until you hit a either one of the players wins or loses. Excuse me. And you would say if whether or not you can guarantee a win would be in the case that one of these branches so one of these choices that you make, you can always win. Yeah. Can you guarantee a win? Well, I think you can, right? How do you... I want to say that you can always... Depending on the state, you always either lose or win, right? That's kind of the deal. You basically want to show that now here's the thing. This is like kind of tricky because you're not just picking randomly. What you're doing is you have a bunch of different choices, and then like it's a little more involved than just the depth first search, because if it's possible to win, that's not the same thing as you're guaranteed to win. Like you make a move, your opponent has a set of choices to make a move, and then you pretty much, you have a little bit of a problem, don't you? Because because your opponent might try to make a move where you can't win anymore, right? Like your opponent isn't going to just randomly select a move. There's a choice that the opponent. So it has to be that for every choice that your opponent makes, they can't win. Yeah, it's kind of tricky. I get tripped up with questions like this. Like I said, the last time I looked at a question like this, it took me forever to kind of figure out how to do it. Because there's a little bit of like finagling you got to do to basically formulate the solution and then code it properly. So like it's not as simple as just recursing on every possibility. You know, like there's sort of a child set that you produce, and you have a state, set the state, recurse in the child set, and then set the state back to what it was, and then you kind of loop, right? Or you loop over all the children by set the state, recurse on the child, and then reset the state back to what it was. And that's every depth first search just has that simple template. But the problem with this is the recursion. It's not. See, the thing is, you maybe want to toggle which player you're looking at. You know, if it's the current player or the other player. Because for the current player, you basically want to find out that that from any move that you make for the current player, that your opponent can't win. Any move that you make that that there is at least one of these moves implies that your opponent cannot win. And similarly, when you recurse from there, that's from your opponent's perspective. Any of the positions that your opponent picks now, you want to guarantee that your opponent can't win. You want to guarantee that the opponent cannot win, but the opponent can pick any of these to try to win. So every choice for the opponent causes the opponent not to win. So it's a little awkward. It's really awkward because this recursive function, I almost want to write two mutually recursive functions that call each other, if that makes sense. One for whoops. Hold on a second. I want to see, what does that do if I click that? Frequent. What I'm almost thinking about doing is writing two mutually exclusive functions, one from the first player's perspective and the other from the other player's perspective, which is kind of challenging. Like, it's a little weird. I don't actually know. And then obviously, ideally, you'd want to memoize all of this, so that way it's pretty efficient. So when you revisit states, you kind of already know. But it's a little strange. Like, I don't know. Because part of me also thinks that really, you're looking at, can you win from this state that you're at, right? There's a base case. We could get that. And then Uh, oh, you know what? I think this routine is actually supposed to be. I want to say, so there's a few things, right? Like, there's one routine that's just the base case, which is you have one move, and in that move you're definitely going to win. But then you have other cases where you have possibly more than one move after that, like the player then gets a move, and then after that you get a move, and you want to see from the state you're looking at, no matter what choice they make, there's a choice that you can make to win the game. Like, these are different, right? The base case, if you can guarantee a win in just one move, then that's obviously a case where you return true and you sort of memoize that state, I guess, which is also a little weird. I don't know exactly how we want to memoize. I think you can use just a map of a vector. I think that works. Yeah, so excuse me. Actually, what is like the equals? Like, what is vector equals? Hold on. There's a bunch of stuff here. There's a few things. So yeah, okay, we can memorize the different states, but the problem is, I guess you want to see the player that's if the next player. I want the function to work where it doesn't necessarily, you don't necessarily care which player is looking at the board. You just want to know if that particular player can guarantee a win. That is to say that the next move, or rather, that is really to say that for all the possible states that could exist, the next player basically can't win. So it's got to be false for all of the next states, and then this would return true, right? If those are all false. Right, and then if those are all false, then this state, right? All the children are all this function called and all the children is false. This state would return true, and then obviously for each of those functions, you have the same routine. It has to be that all of the children, in order for that to return true, all of the children have to be false. If there's one child that's true, then this one returns false. And then there's one child there that's true only if all the children there are false, if that makes sense. So that's a tricky thing. Now, what's weird about that too, on top of it, is all of the children being false at the bottom. It's kind of weird because there's sort of this like true false thing going on, changing of states, and the only way for it to be false for every possible move, I think, is if there are no moves. Yeah. Yeah, so if there just aren't any moves, then you return false. Then that player lost. That player can't win. The game ends when a person can no longer make a move. So if there are no more moves, that's false. If there is a move, if there's only one move, well, no, that's it actually. The base case is really that there's no moves, and you return false in that case. However, if all of the children are false, right? In other words, you make a move and then there are no moves, then that actually is true. Then you actually won. And if you can guarantee your opponent can't. Yeah, it's really funky. Really interesting, but super funky. But we can do it that way. So let's try that. All right. But I think that's kind of how, that's sort of how you would normally handle. The reason why I'm kind of like really going into depth about this is I think this is how you would handle games in general, like a depth first search over game states in general. Is you could do it like this. You could actually use a function like this. Now, mind you, and it's kind of irrespective of the game. Like there's a certain abstraction where it doesn't really matter what the game is that you can use a search function, sort of a min-max like search function like this, where it doesn't, instead of being no more moves, it could just be like, yeah, no more possible moves, or it could be a game state position where like there's a certain, like the base case could be you certainly win in certain cases, something like that. Like the winning condition here is that there aren't any more moves. So and the winning condition is that the other player doesn't have any more moves, which is a little bit kind of like the logic there is like a little bit funky. But I mean, practicing these problems helps a lot, right? Like going through the different possibilities, I guess, is or going through different problems and like how you might program them is going through the different problems and going through the different problems and coding and thinking about different kind of game related problems will give you some experience to draw from to possibly, when you see a similar related problem, to be able to kind of quickly come up with the answer, quickly come up with a similar kind of a template. I think that's, yeah. So I think like experience will help a lot with that. Like the template, because the template kind of gets modified a bit depending on like the winning, how you win the game. But there's sort of a generalizability. There's some degree of like generalizability that like games that have two players, you kind of have this like back and forth where you can sort of write your function, so something like this. Yeah. So we want. We don't really need anything, right? Like this is going to just be the DFS of DFS, and we're going to write it this way. We're going to sort of keep most of the state here. So this initial state, and we'll say if there's a move. So the move set, the children. Rate over child set. So actually this one is super interesting because it basically always returns false, except you have like a routine that if all of them, so we'll have really a check here, or we'll do ret. I don't know. We'll figure that out in a second. I'll explain that in a moment. We'll figure that out next. But the child set is going to be, you have the state that you're in, and you want to make a move on that state. So now, fortunately, the size doesn't change. Yeah. So what do? Is an index. It's an index. We don't want to use pointers because it gets a little confusing with pointers as things get modified, things get changed. So we use indices. I don't think pointers are fine. I think pointers are okay. It's just yeah. I think pointers would work. It's just it can get a little funky with pointers because or iterators rather. Let's try with iterators. Let's try. Let's just see what that looks like with iterators. So auto it equals state.begin. Yeah, in the beginning, and then it's not going to be the end. And we really want to say -1, right? Give ourselves a little bit of room. Character A, it, and then B equals it plus 1. And we say if A equals a plus symbol and B equals a plus symbol, then we have a move we can make, right? Okay. Then what we're going to do is we're going to set it of, we're going to modify this position. So auto, really, we already know though. Yeah, we know what we're going to set it back to, so we don't have to do that. So we do want to do this though. Temp, yeah, we want to save the iterator. And we're going to say it to subtraction and it plus 1 to minus symbol. We're going to call our DFF or f of f, and then we're going to set these back. It equal temp, and then same thing. Yeah, because this iterator, we want to set this. We want this to be in the right spot. I don't know if this is necessary. This may not be, but we're gonna do that just to be careful and set this back to what it was. So these are all the children, right? This is it. We're gonna loop over all the children and recurse. And there's one additional piece here is that you only return true if all the children return false, right? So true, and then we say ret and equals, say, return true if and only if all the children return false. So we recurse on all the children. So we ret n equals true. You just don't want to do, they're all false, so they're all not, right? All not true. And then after you go through all the children, you would return ret, right? You would say it's initially true, and then they all have to be false to keep ret true, otherwise it turns to false, right? And that's pretty straightforward. And then you also have, by the way, you could say the value is f of f, and you just say you want ret is going to be and equals the negation of this value. And we could terminate early. We could say if value, then return. So if this value is true, so all the children have to be false. If any of them are true, then we just return false immediately. Right, so we could terminate early. So if any of the children are true, immediately you can't guarantee a victory. So you return false. Very interesting. So let's do it that way. And you also want to memoize. Yeah, we'll say memo of the state is going to be false, and memo of ret is going to be, or ret of the state is going to be ret, whatever that is. And we say memoize. That's one base case we need. So if memo.count of the state exists, then return memo of the state. And let's see what that happens here. True. Minus minus, minus minus, minus minus. Something like this, something like this. Let's just see what happens here. See if we get runtime errors, time limit exceeded or anything like that. Oh, nice. Okay. It's correct and quick. Correct and quick about it. Oops. It says 0. It doesn't say if it's correct or not. It just says 0 runtime. Diff. Oh. It's wrong. What? What is going on? Oh, that's confusing. It doesn't say if I'm wrong or I'm right. It just gives me... What? Let's try this. Hello? Wrong. Alright, that's good. It's good that we're wrong. And it tells us. Well, that's not good, but... So... Guarantee you win by flipping the middle. Okay. So we got... All of them are wrong. False, true, false, true. Okay, interesting. So this one we got false, right? And it's... Why is that? Right over the child set. Call f of f. If val is true, and this has got to return false. So what happened? We got expected true, output false. Why did we get false? Game ends when a person can no longer make a move for the punishment guarantee a win. If the starting player can guarantee a win. So the starting player in this state can set this plus plus to minus minus, and the next player basically, oh, this should be false initially. Or If there are no moves, it doesn't return true, it's return false. And there's at least one move. Aha. That's, we gotta be careful. Can move equals initially false. There we go. Yeah. Can move is false, and we say if these things are true, we set can move equal to true. Yeah. We don't unset that either. It just gets set once. Does that work? That might be a little confusing. That's better. Okay. These other test cases. If you don't have any moves at all, then you lost, right? Difference. The bottom two, top one is true and true. What is going on, man? What is going on? Hello? Wrong answer. Nice. Nice. What do you mean false? What? What is this? What? What? Oh, you gotta be kidding me. Nice. Very good. That's what I like to see. Huh. So, in this first case, alright, well, this is awkward. It's taking me a lot longer than I thought it would too. In the first case, you can make a move. You go minus, minus, and then the next case, so you make a move, and then the next case, the child, so you make a move. You have 1, 2, 3 moves. So can move is true, right? Ret's true initially. Every one of these moves, 1, 2, and 3, all of those moves should give you false, right? If you make a move on the left side, make a move on the right side. Oh, well, I guess. See, that's the thing that's throwing me off, right? That's why I feel like I need two functions, two mutually recursive functions. Like I need another function definition where you have each of these different board states that they're looking at. I don't think it's enough for just this function to figure this out. That's what I want to. That's why I'm thinking like you want to have a function for like each player, you know, and if there's overlap, then you can combine it. But if there's not, and you can't combine it, then that's just it, right? You should use That's what I was saying before about like this being kind of tricky. That's why I think more experience with these kinds of questions would help. I think. Especially considering I haven't even been able to figure out this one. Yeah, because you're trying to recurse with just one function, and it's like that's probably not. That's probably not the way to do it. You can guarantee a win if there's some board state. I want to say that this is not. I want to say I'm wrong about this. I want to say that if all the children return false, I want to say that's only if any of the children return false, right? So if it's not possible for your opponent to win at all, then that means that it is possible to win, to guarantee a win. See, there's a difference between guarantee a win and potentially win. Yeah, which is why I think it's going to be kind of, I don't think it's going to work properly, right? Because now I have two different functions. I have, you can guarantee a win if for every possible board state after you move that your opponent cannot win, right? That's what I had initially here. But really, it's, you make a move, because any of these board states, it's actually, if any of the board states where your opponent can't win, then that means you can guarantee a win. It's not all of them. It just has to be, you only pick one. You pick one board state, and they can't win from there, you're in good shape. However, from there, so you're looking for one false somewhere in this sea of truths. From that position, your opponent is looking at the same thing. All the children there just need to find one false where you can't win from that child, where the can win is false, and then that's true. Super confusing, but I think it's at least one. At least one of the children return false. In which case, we can go back to what we were saying before about being able to move. If there are no children, then it's actually initially false. So turn true if and only if at least one of the children return false. So we say or equals. And actually in this case, yeah, this terminates early too. The negation. Yeah. Just say if ret then memo of state equals. Oh, there's a problem here too because the state is wrong. I think we don't memoize this part. I think we just return. That might be part of it too. I don't know. That's super confusing. I don't know, man. Because the memoizing the state. Oh, I've done this before too. Deja vu, man. Deja vu. When you change the state and then memoize the change state, it's super easy to forget that. Let's go all the way back. What if we just don't memoize here, right? What happens when we do that? I think it's still wrong, yeah. I think the logic is still wrong. But at least we could say it's just always false. If there aren't any moves, return false. As any of the children, return false. And then if ret would return true. How about that? How about that? Still wrong. Nice. Nice. What? Any of the children return false. Return true. Red is false. Take the negation of f of f. Return true. Really? No. No. What? What? What in tarnation? What in tarnation? Yeah, still the top level. Why do we get false? It should be, if any of them are true, this will return true. Oh, I'm sorry. No, if any of them are false, I think. You could make this move, first move, and then that state. So it's true, false, true, right? True, false, true. If this is output true, we expect it true. No. Wait. All these states, we got true, false, true. Those are all the choices. And we said if any of those are true, or equals, if any of them are false, which this one's false, right? Middle one's false, which is exactly what we were thinking. Any of them are false, then this returns true. How did we make a mistake? What happened? Really? No. No. Oh, something went wrong. Something went wrong. Okay. All right, let's do this. What does that do? Does that give us the output we want? State result. Okay, because we want brother, this would not be this would not be a good question for me during an interview. I would get destroyed. Output false, expected true. What? Wait, what? No. Shouldn't these? What happened? What happened to? Oh, no. What? I am so confused. So, oh. No, it doesn't matter. was gonna say we should go left to right, but actually it doesn't matter. It's just I'm just really confused. What? State minus 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 result 0 minus 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 0 false false. Oh, that's why. Duh. Sorry. Recursion. There we go. Alright, anyway, doesn't matter, right? We're not seeing all the states here, so minus minus plus plus. How many times are we calling f? What in darnation? So yeah, so we minus minus here, plus plus, and then we recurse, print out the state. We don't need to print this one. That's just confusing. Print the state after the recursion. You really should print the state before the recursion, I think. I don't even know. Huh. Excuse me. I think I actually probably want to go down here. Let's not terminate early either, just for the sake of keeping things clear. Oh, gives us the right answer now. What? Wait a second, what? What? Ooh. Excuse me. Wait a minute. Really? That's why? That's the problem? That doesn't seem... That's a little weird. So, yeah, I mean... Call this not equals, right? Reset the state. Excuse me. Yeah, so these are basically going to be printing backwards, though. So we got a 1 for all 4. No, that's so confusing, man. This is like... Well, yeah. Uh-huh. What? No. Because the problem is that we're going to be printing the result after the recursion, so we'll have the state before we call the recursion, and then afterwards we call this recursive thing. And then I guess that's probably why this isn't working properly, is because terminating early doesn't really make sense. Possibly, I guess. I don't know. I don't know, man. I don't know, man. Excuse me. I don't know, man. I don't know. This is interesting. This is interesting. Seems to cause problems. This seems to cause problems. Now that I don't understand. I don't know why that's causing problems. Couldn't tell you. That doesn't make any sense to me. That's one thing. And the other thing is, what is this even printing? I don't know what I'm looking at anymore, man. I don't know. I don't know. Figure out what X was. Excuse me. Maybe you do this before you set it back. Before you set the state back, we'll take a look and see. What was this? So all minus results 0, so false. No moves can be made. One move can be made here. You can win here. Here, no moves can be made. So lose, win, lose, lose, win. And we're saying if any of these, really these three, if any of these bad boys, 1, 2, 3, if any of these return false, return 0, then we return true. However, now here's the interesting part. Oh, I think the reason is that you need to reset the state. Yeah, that might be why. Because I think this cascades upwards, and you need to memoize the state properly. Can we do that? Basically break from this loop. Could alternatively just say break. How about that? Okay, yeah, that's what we're after. That makes sense. There you go. There we go. Right, we got here, we got this is, yeah, okay. That's all the information we need at that point. All the information we need. Or even return true, right? Now let's see if we do that, what happens. Yeah, I think it's okay. Break is probably simpler. Same thing. Okay. Interesting. Yeah, man, recursion, tons of fun. Definitely does some interesting things. Recursion is very interesting. TLE, nice. Time limit exceeded. Perfect. Perfect. Well, okay. Kind of what I would expect. I guess what's interesting about that is, yeah, this is it's quite the algorithm here. It's quite the algorithm here. I believe it's exponential. 92 milliseconds. Okay, watch this. Add one more plus sign. one more plus, or one. I don't know how many added. One. Okay. How about one more? Uno más. Uno más. 124. Okay. One more. One more. Here we go. The roller coaster ride. 768. Output false. Expected. Yeah. Yeah. Alright. Now, what I want to do, I bet we're going to just return false every time, right? I bet you they don't have, it doesn't say wrong or right. I think this output is too big. I think their program also times out. That's what I was gonna say. I was like, how come I'm not getting a wrong or right here? It's not my algorithm. My algorithm just returns false. It's theirs that's taking too much time. See that? It doesn't say wrong or right. There's no note on how far you can go. You see that? That's why. That's interesting. That's fun. I see. I think that they don't have an efficient algorithm for this one. Something like that. I don't know. Let's try a bunch of random stuff. Oops. Alright, what happens if we do this? What happens? What happens if we do this, eh? What happens if we do this, eh? Yeah, what I think is happening. What I think is happening is it's pretty good. This is pretty good. It's pretty good. Hold on. wait. I'm having a good time, man. I like having all. Oh no, really? What? Oh, all right, fine. Having a good time. I think, like I said, I think the test cases they have aren't super large. I think they're pretty small. And one more issue is why? What are we expecting with this? What do we expect with this? Empty string. Should be false. Okay, should be able to handle an empty string. All right. We can, a couple of things we can do. We can put like an edge case here, or we can modify this so. Oh. I mean, you could do both. Should handle that case. Yeah. Very subtle thing there. All right, let's go for it. Hey, got there. Sweet. Nice. All right. Runtime, analyze the time complexity of your algorithm. No. What? Why did I do that? What's wrong with you? What do you mean? What do you mean? Derive its runtime complexity? Are you kidding me? Is that a joke? Is that a joke? It's expensive. it's non-polynomial. It's basically, there's a branching factor that happens here where it's you're recursing. You have a branching factor that decreases by 1 at each step. So of all the possible moves, the first board state, every possible move, and that creates another board state to recurse on. And then for each of those board states, there's at least one less move that you can make, possibly 2 less moves. So then you multiply by either n minus 1 or n minus 2, where n is the number of states you had before, and then you just keep multiplying. It's effectively factorial. It's effectively factorial complexity. However, not necessarily, because there's also terminates early, so it's not completely, like a lot of cases it's faster than that. It's definitely non-polynomial though. That's probably the easiest thing I could say. It's definitely non-polynomial. But that doesn't matter because all the test cases are pretty small, as you saw. It's a pretty interesting question. It took me a really long time to kind of work that through. Probably like medium questions, I think I should be at the point where I can do them. I can't do all of them in 5 minutes, but a lot of them I can do in about 5 minutes. These kinds of questions are pretty tricky. The ones that have basically you have to write a search algorithm, like a backtracking search algorithm, or a depth first search kind of approach, because they can be kind of tricky to get right, to kind of formulate in a way where you can get the logic correct. As you saw, I really struggled with that. The terminating early was causing a lot of problems. And then, it's pretty. It's really simple what we're doing here, if you think about it. But it can definitely be hard to get there quickly. Let's say it can be challenging. Now, what's interesting about questions like this for a bonus, more likely than not, this question. Oh, did my camera? Hey, hi, bud. My camera having an issue here? I'm sorry, I didn't realize. I can fix that now. Oh no, really? Hello? Camera, wake up. Wake up. Wake up. Appa. Oh, maybe it was just covered with schmutz. Maybe it was just dirty. I'm sorry. I realized how much junk was on my camera. Oh, okay. Well, anyway. You get to see this beautiful light shining here, like I'm freaking. It's good. It's good. It's good to get some light. Anyway, yeah. So, part of the problem with this question is, the discussion. Yeah, let's take a look. Other people definitely have some backtracking. Yeah, memoization. Python. Whoa. Backtracking. 3 lines in Python. Are you kidding? Guarantee a win equivalent to win. Yeah, see, that's what I got hooked up on, or I got stuck on. DFS. Can you improve the time efficiency asked by the recruiter? Exponential versus factorial. Okay, let's read the theory part. First glance, backtracking seems to be the only feasible solution to this problem. We can basically try every possible move with the first player, call him P1P from now on. Recursively check if the second player has any chance to win. If 2P is guaranteed to lose, then we know the current move 1P must be the winning move. The naive implementation is actually very simple. Booyakasha. Alright, that's pretty much what I did. Yeah, it's super straightforward. Probably I could have done this a little bit more cleanly, I guess. You leave the string as it is, I suppose. Oh, that's interesting. You overload can't. Oh, I don't do that. I don't take advantage. That's fun. I like that. Take advantage of the can't win. of the overloading. Actually, that's what that is. Overloading. Oh, that's neat. That's kind of nifty. Put this in the. I wouldn't personally. I wouldn't do that though. That's not really my style. But that is interesting. Didn't memoize this at all either, huh? There's a few pieces missing. The memoization is missing. And then also it made it really simple to, when you return not if wins, turn true, otherwise false. I like this though. I mean, I like this implementation. It's pretty neat. Pretty neat. Pretty neat. But yeah, I mean, yeah, I don't actually need to update the pointer as I did before on the stack. I can remove that. Thinking about it now, the reason being this part's unnecessary, and the reason for that is what did he do here? He did something. Yeah, he put these on the same line. I mean, I'm not really a fan of doing that either. It's one way of doing it, but I wouldn't. The reason why you don't need to do what I was describing, where you put that pointer on the stack, is because it's not necessary because of this is already on the stack. This iterator, this value, when you call this, it gets pushed on the call stack. When you come back, it comes back from the call stack. So you shouldn't need to do that. It should already be kind of, still in the, should already be in the right spot. Yeah. And simple memoization. I really didn't add very much other than I modified the state because I didn't want to modify the string. And I wanted to memoize the state, which, I mean, you could technically memoize the string, but string memoization is kind of slow. It's kind of slow. So, yeah, and obviously with iterators, you kind of have to be a little bit careful. There's another way to do this too, which I like, which is if you take the end state and you subtract the iterator, and you say it's got to be greater than or equal to, or less than or equal to, I don't know, the size. So really, we want this to be greater than or equal to 2, I think. There's another way to do this. Does that work? Yeah. It's a little more math there. But this is, if you have some let's say you want to have 3 or 4 consecutive things, this is a little bit easier to remember, a little bit shorter than the other one. Although it looks like it's slower. Is that true? Is this slower than doing these 2 comparisons? It's about the same speed. Interesting. I like doing this one more. I like instead of using the and, I like using the I like using this too. Yeah. Reason being, it's just kind of easier to remember, I guess. Iterator sizes and amounts, I guess. Yeah. Yeah, not just easier to remember, but this is like way better for arbitrarily long consecutive sequences. Like, excuse me, normally, like you would do something similar for loops, where if you like, you only want to go halfway through the loop or something. With iterators, it's a little tricky, but in this case, we have random iterators, randomly accessible iterators or random access iterators, so we can just subtract them to find the size, and then you just modify this conditional slightly so that way you can say like, okay, we need at least 2 elements left, or at least, you know, whatever, for this to work properly. Yeah. Okay. What is the rest of the discussion here? Excuse me. So yeah, I mean, sure. You know, I could probably scrunch this all together. I have pretty much the same code here, except one little extra. I have a memoization down here, and then I set up an initial state, some code to memoize an initial state, and like breaking out of this to terminate early rather than just returning true. Time complexity, only plus signs. We have roughly O of n factorial. Is that factorial? I don't know why it's 2 of these, but anyway, roughly n factorial. Optimize with memoization, true. Can we even do better than that? Sure. Below I'll show the time complexity can be reduced to quadratic time using dynamic programming, but the improved method requires some non-trivial understanding of the game theory and therefore is not expected in a real interview. If you are not interested, please simply skip the rest of the article. Now, this is when you're interviewing in 2018. All right, that was 3 years ago, okay? The world has progressed, all right? If you're in an interview, you need to know all of game theory. Just kidding. I don't know. You probably don't need to know this in an interview. But what's interesting is, this memoization, I believe, actually gives you quadratic time. Could be wrong, but I think it does. Could be wrong about that. What they're saying is you can actually use some game theory shenanigans to go to quadratic time. Now this is it's about to get a little too funky, a little funky for me. Stellari is back. Backtracking to DP in 0 milliseconds. I guess the backtracking is not the same thing as the DP. I guess not. Maybe I'm wrong. I don't know. I feel like a lot of the backtracking algorithms are. No, yeah, I am wrong. I'm sorry, I am wrong, because even though you memoize your backtracking algorithm, it's not necessarily. Yeah, it's a form of dynamic programming, but it's not. It's not the same thing, because if you do like a dynamic programming solution where you have like n iterations, at each iteration you do exactly n calls that are memoized, that would give you quadratic time. However, in this instance, it's not obvious or clear how many iterations we're doing at each step, and I think it's fair to say that we're probably still exponential time or factorial time, except probably still factorial time, except now it's memoized, it's a lot faster. I want to say something like that. Can we do even better than that? Sure. Below show the time complexity can be reduced to quadratic time using dynamic programming, but the improved method requires some non-trivial understanding of the game theory, and therefore is not expected in a real interview. If you are not interested, please simply skip the rest of the article. Right. So this is the game theory stuff. So game theory, this is the game theory stuff. So game theory, often two-player games, you can apply game theory to those games and come up with some interesting maths, interesting results, and usually they're useful for these kinds of questions, kinds of problems. Given a particular arrangement of the game board, if either player have exactly the same set of moves, should he move first, and both players have exactly the same winning condition, then this game is called an impartial game. For example, chess is not impartial because the players can control only their own pieces, and the plus-minus flip game, on the other hand, is impartial. Yeah, so that's actually also one of the reasons why I think this works out nicely for like a simple recursion and a simple like using depth first search with only one function, right? Because that board state, as you saw, the can win really, it doesn't care which player is looking at the board state. If you're trying to figure out, can this player win, yes or no, right? From this position, and basically that means that you control all of the pieces in the board state, and your opponent has control, when it's their turn, has control of all of the pieces in the board state. So you're both basically looking at the same state each time, but you're both looking for different objectives for that state. So that's pretty interesting. But yeah, I was trying. I didn't, I hadn't articulated that, but that's what I was noticing. Yeah. Normal play versus misery play. Nice. Misery play. The winning condition of the game is that the opponent has no valid moves, then this game is said to follow the normal play convention. If alternatively, the winning condition is that the player himself has no valid moves, then the game is called misery game. Our plus-minus flip has apparently normal play. They literally call it misery play. Misère play. What is that? How do we? The miser. Destitution. Oh boy. Being that I'm not French, I would call it misère, or battle. Conventional rules, except that it is played to lose. That is, the winner is the one who loses according to the normal game rules. Or if the game is for more than two players, the one who wins according to the normal game rules loses. Such games generally have rule sets that normally encourage players to win. For example, most variations of droughts, known as checkers, in the United States require players to make a capture move if it is available. Thus, in the misère variation, players can force their opponents to take numerous checkers through intentionally poor play. So one who loses. So if you lose all of your pieces, so you could play misère version of checkers. That's fun. Combinatorial game theory. Misère game is one played according to the misère play condition. That is, a player unable to move wins. This is opposed to the normal play condition in which a player unable to move loses. For most games, this is the same as the ordinary use of the word, but a very few games are actually misère games according to their standard rules. For example, silver coinage. Okay. Nim, often played using the misère play condition. Last year at Marienbad. I am familiar with Nim because of the question that I'd solved all these years ago. Now that was regarding Project Euler 411, something like that, 412 I think, and that was a Nim question, and that's probably the hardest problem I've solved in my life. It's kind of sad that that's not even ranked the highest difficulty. It's just like pretty hard, but I just really had a hard time. It's actually not even really that hard of a question. If you know a little bit of game theory, it's pretty manageable. Perhaps the only misère combinatorial game played competitively is in an organized forum is Sprouts. Low ball, form of poker. Lowest scoring hand wins. Interesting. Losing chess. Avoider enforcer. Natacto. Miser. Miser is a person who is reluctant to spend, sometimes to the point of foregoing even basic comforts and some necessities. Oh, is that what they call it? Or to hoard money or other possessions. Is that when you just can't afford it? Yeah, I'm pretty miserly when it comes to money. Like, pretty gross. It's pretty frustrating. It's pretty gross. It's pretty frustrating. It's like it's aggravating, actually. Think about it. I'm just freaking broke, you know? Freaking broke. I'm not even broke. I'm in so much debt that it's like, how do I not be a miser? French for destitution. Oh man. Oh, what a word. What a word. Just, okay, anyway. How do you say it though? How do you pronounce it? That's what I'm looking for. I just want to know how to pronounce it. Do we have a button? How to pronounce? Come on, no. Mesure, I don't know, mesure. Love words? Sure. Of course, why not? I'm looking for the pronunciation. Rhymes. What does it rhyme with? Mesure? I don't know what that is. One syllable. Air. Okay. Air, bear, Blair, Brer, care, share, crayer. What is that? Lair, hair, glare, flare. Okay. So it rhymes with misère. Okay, so it rhymes with that. Misère. Interesting. Misère game. Alright, anyway. Okay, back to studying here. This is a misère game. Alright. Apparently has normal play. Got it. That makes sense. Yeah, it does seem like this is normal play. Also, I'm thinking maybe I'll lower the volume a little bit, just because I'm talking kind of at a normal tone. I do like to keep my voice down generally, but I noticed I'm speaking kind of loudly here. So misère. Now we understand the flip game is an impartial game under normal play. Luckily, this type of game has been extensively studied. Huzzah! Note that our following discussion only applies to normal impartial games. In order to simplify the solution, we still need to understand one more concept. Concept 3, Sprague-Grundy function. Suppose x represents a particular arrangement of board, and x sub 0, x sub 1, x sub k represent the board after a valid move. And we define the Sprague-Grundy function as g of x is the first missing number of g of x0, g of x1, g of x2, ... g of x sub k. Where first missing number y stands for the smallest positive number that is not in set y. For instance, if g of x equals 0, g of x1 equals 0, g of xk equals 2, then g of x of first missing value is 0, 0, 2 is 1. And that's the Sprague-Grundy function. No kidding. Whoa! That's quite the function you got there. What is that thing? What is that thing? What? That's new to me. What the heck is that? Is that even defined for? What is that? I mean, there's so many questions I have about that. What is that? Where does that come from? Why that? What does that have to do with what we're doing? Is that even defined on every number, like how many numbers? These are, what is happening? These are different board states, right? So g of x is just some board state. It's the first, so you need an ordering of some kind for your board states, no? Because this is numbers, but I guess you have to make your, I guess you have to value your board states now, or give a value to your board state. That's super interesting, but yeah, why do we need this bizarre looking function? Yeah, it's really bizarre, because it seems like it's only defined for, I guess you have to define these, I guess you have to define G for like initial values or something. You know, like it's very, you have to actually give numbers, you have to give an evaluation of the board state, something like that. Something like that, I don't know. It's definitely like not the most obvious thing what this means. Pretty interesting though. Why do we need this bizarre looking SG function? Because we can instantly decide whether player 1 has a winning move simply by looking at its value. I don't want to write a book out of it. Okay, so for now, please simply take the following theorem for granted. If g of x is not equal to 0, then first player must have a guaranteed winning move from a board state x. Otherwise, no matter how first player moves, second player must then have a winning move. So if this is not 0, first missing number is not 0, then this player has a guaranteed winning move from this board state. Otherwise, no matter how this first player moves, the second player must then have a winning move. And that's apparently a theorem. Alright, take it for granted. I can't. Impossible. I need to know why. Can't just take it for granted. That's not, Impossible. No. Cannot take it for granted. Absolutely not. Trust only God, all of this big data. No, I'm just joking. I don't want to take it for granted. However, for the sake of discussion, I will take it for granted. Oh, I shall. So our task now is to calculate G of the board. But how to do that? Let's first of all find a way to numerically describe the board. Since we can only flip positives to negatives, then apparently we only need to write down the lengths of consecutive positives of length greater than or equal to 2 to define a board. For instance, 2 can be represented as 2, 4. 2, 4 has 2 separate positive sequences, subsequences. Consecutive subsequences, you mean, or contiguous subsequences. Oh, I see. Okay. I'll need to write down the lengths of the consecutive double pluses greater than or equal to 2 to define a board. Okay, I guess that makes sense. Yeah, because if they're separated by 1 minus or 2 minus characters, then really don't care, right? It doesn't matter. It's kind of the same board state anyway. Interesting. Any operation made on one subsequence does not interfere with the state of the other. Therefore, we say 2, 4 consists of 2 subgames, 2 and 4. Okay, yeah, that's interesting. That's fair. That's very interesting. Okay, now we are only one more theorem away from the solution. This is the last theorem, I promise. Sprague-Grundy theorem. The SG function of game x is equal to S1, S2, S sub k equals the XOR of all its subgames, S sub 1, S sub 2, S sub k. Example given, G of S1, S2, S3 is equal to GS1 XOR GS2 XOR GS3. Oh, no kidding. Wow. Another game theory result that I would want to see the proof for. I need the proof. I need the proof. Gotta see the proof. I gotta see the proof. Interesting. Qué interesante. Qué interesante. Muchos interesante. Muchos interesting. SG function of game X equals S sub 1 to S sub K equals the XOR of all its subgames. S sub 1 to S sub K. G of S sub 1, S sub 2, S sub 3. So the SG function of a game X, which is a bunch of subgames, is the XOR is equal to the XOR of all of its subgames of the same function of applied to each subgame. Brother, this is going to take me a lot of time to figure out, to understand what are we talking about here. What are we talking about? So if a game is normal and impartial, then you can apply Sprague-Grundy theorem to get some interesting results. Interesting. With the SG theorem, we can now compute any arbitrary gx. If x contains only one number n, there is only one plus subsequence, then x contains only one number n, there is only one subsequence, then f of mv is, or g of x is okay, it's g of 0n minus 2, 1n minus 3, 2n minus 4, g of n over 2 minus 1, n over 2 minus 2. I think he may have mistyped something. Oh, no, wait. 0, n minus 2. 1, n minus 3. Oh, I see. I understand now. He's representing the board as, he creates two subgames each time. I think I get it now. Yeah. So subgame with 0, right? Sequence 0 and, okay, I understand. These are sequences. So here's the sequence. So basically there's a whole bunch of board states after a move, which is this guy over here, and we get our FMV of these G's, and now he's, okay, I understand now. So, excuse me. So then you go all the way up to halfway through, because then when you start going the other way, the sequences, we can actually order the sequences. You actually start going, it's symmetric. You start going, you have the same numbers again. So you don't need to double check all those, right? Assuming this, it's a function, so it's going to return the same value for the same input. And the inputs, it's not ordered, it's a set, basically, a subsequence, or it's a set of, yeah. Well, actually, because I shouldn't say it's a set. It becomes like a set because it's not a set. It's set like. It's because of this theorem. These subgames being subgames, you can actually swap them, and you'll get the x, because the XOR is commutative. The XOR function is commutative. So any ordering is going to be equivalent g of, any. It's not that it's a set, because that would imply that you actually remove some possible results or board states, but or potential values that would be a part of the board state, but that's actually not the case. They're just commutative, these values within the input. So that's why it only goes through halfway through. And then he says, oh, because of that, this theorem, not only are these commutative, well, I mean, they are commutative, that's why you don't use all of these, but you can now rewrite them as the XORs of each of these. These are become subgames. XOR value of each subgame. That's super interesting. Wow. And then this should also be XOR, right? Again. So you have a recursive definition for g of x now, which looks like f of mv. And here you go. Here's sort of like the recursive definition. And now you want to compute this definition using dynamic programming. Dynamic programming, because you do have, for G, you do have a base case. Now we have the whole algorithm. Convert the board to numerical representation. X equals S sub 1 to S sub k. Calculate G of 0 to G of max S of I using dynamic programming. If G of S of 1, G of S of 2, XOR, etc. is not equal to 0, return true, otherwise return false. So now the question is, if G is not equal to 0, return true, which is the first theorem up here, which is if G is not equal to 0, player 1 has a winning move, otherwise player 2 has a winning move. So if this is not equal to 0, return true, otherwise return false. Calculating G of n takes O of n time. And over to XOR operations plus O of n, first missing number algorithm. Right. If you have the previous values, it takes O of n time. And we must calculate from G of 1 all the way to G of n. So overall the algorithm has O of n squared time complexity. Naturally the code is a bit more complicated in the backtrack conversion, but it reduces the running time from about 128 milliseconds to less than 1 millisecond. Huge improvement, is definitely worth all the hassle we went through. Yeah, that's pretty wild. That's definitely. This is like, it's kind of funny. It says it's a little more complicated. This is like how my code normally looks though. Like this is like how I normally write code. It's not. Oh, to you it's more complicated. Okay. That's like how my normal solution looks. That's pretty amazing though. That's pretty good. It's pretty good. Let's see if we can write something similar. Let's see if we can write something similar using this XOR function. Numerical representation, board states. So finding this first missing number algorithm, though, we have to think about that. That's the smallest positive number that is not in set Y. Okay. Interesting. So that's probably the only little. So we'd write like a subroutine. So let's try to implement this from now that we understand what was being suggested. So this is an impartial game. Hold on, as described. It's pretty wild. This is pretty wild, man. I probably should learn more about game theory if I want to mess around with combinatorics questions that have, involve games. I like this question a lot, though. It's really good. I like this answer a lot too. So what we're looking for, it's an impartial game and it's played normally, right? So I guess every impartial game that's played normally has a similar, now here's the tricky thing. It's not totally similar. It just so happens that in this case, there's an easy way, each move it's easy to kind of figure out what the subgames look like for each move, which is not always true. It's not always true that you can have these easy to sort of figure out subgames. So it kind of works out really nicely for this game, but that may not always be true. Even though it's impartial and normal, it's not necessarily, there are some components about the game itself that make it easier to work with, I guess. So this isn't too hard to kind of go back to. So let me submit this one more time for good measure. And then and now we're going to go right. Let me think about it here, see if we can get this. All right, we definitely want our FMV first missing number algorithm, which should be interesting. We want a set of numbers. It's the first number that's not in the set. That's pretty interesting. How does that work? It's the first missing value. Smallest positive number that is not in set Y. It's literally the smallest positive number that's not in the set. That's it. Like that's the whole. No kidding. And you're saying it takes linear time to figure that out? Really? Is that true? Is that even? I mean, yeah, well, okay. I mean, I guess it makes sense. Is there a way to do, I mean, yeah, all right, sure. You just use a hash set, I think. I don't know. Let's call it X. Literally just for int I equals 0 or I equals 1. I is less than x dot size plus I. If x dot count of I equals 0, return I, return that size. I think that's why it's linear time, right? Because, I mean, given that, supposing you have that set, basically you're going to take a look to see, if as I in the set is 1 in the set, and then you go all the way up to 1, 2, 3, etc., all the way up to the size of the set. There's n elements in the set. If they're all 1 all the way up to n, then it's actually equal to the size, and then it's going to be x size plus 1. Right? In other words, if you have all of 1 plus n all the way up there into the set, I mean, you have to hit at some point the sort of open hole, quote unquote, opening. And the reason why you have to hit that at some point is because pigeonhole principle, basically, that once you check more than n numbers, you can't have more than n consecutive numbers in a set if there's only n numbers in the set. So once you get all at the edge, then obviously you're just the size plus 1. But you're as you're checking, basically you'll hit the hole, so to speak, because you're just going consecutively from one to the end. So this should work. Pretty interesting. Yeah, we'll use sets. I was thinking maybe you could use vectors somehow, but I don't know. I'm not sure about that. So we have this first. So I see why this is linear time too. That makes sense. The next thing would be the. Okay, so we have that, and then we say, basically, our function is going to be a recursion on all of the possible board states. Then you just call this on the result of all those possible board states. You basically create an unordered set out of those states. And it's actually not going to be the unordered set, because you can have multiple values in this set. Which is a little confusing. No, so as far as this function is concerned, we don't care if we're losing numbers or not in the set. But as far as like taking XORs of functions, that does matter. We're going to want a vector of ints. Call this dp. And the size is going to be, I guess initially be 0. Start off with 0. I don't know if this is true or false that we want. We do have to consider, so we have this recursive definition, but we're saying if it's not equal to 0, return true, otherwise return false. So these, we have to basically score the board state. But what do we, like g of 0, do we give it, I guess we give them 1s or 0s, really. I think it could just be true or false, I want to say, because what do we really need for the scores? Scores for the board state. It doesn't really matter that much, I think. And then we'll say n is, right, the way we're going to represent this is if you have, it's the size of the pluses and minuses, I guess, so the size of the consecutive pluses, which could be 0 or could go all the way to the string size, which is, so we'll do string.size. So this will have the same size, the string size, and we'll do +1 just for good measure. Right, we'll do it that way. And then we're gonna say simple routine. Hopefully this makes sense. dp of string size. We're going to say int I equals 0, I is less than string less than equal to size plus I, and we want to have an initial value, some initial state, because we're going to get all these subsequences. We want to calculate those. We have all these sub games. Yeah. So we call this, is this first missing number of a set. We have to provide the set. The set's going to be all of the possible board states. So we're gonna collect the board states, which are actually, so here we're gonna do collect board states and the into a set. And then dp of I is going to be first missing number of these are actually going to be booleans, I think, not integers, by the way. Maybe they should just be integers, right? Because I don't really know. Make them zeros to begin with. Whatever, we could always go back to booleans if it doesn't work properly. Actually, it's not just this. It's if this is not equal to 0, return true. Otherwise, return false. So what do I want to call this? Board states. Collect board states into a set. So we'll just say states or states values or state values, something like that. And we'll figure that out in a second, but we'll do the find missing number of these state values for I, and that should be enough, or not enough, but we're not quite there yet. There are a couple things. Collecting the state values is meaningful, but you're going to dp of I right to the missing state value, first missing number. Okay. Now dp of 0. So let's start with collecting the state values. So for some random I, what you have is dp. It's a loop, right, of a whole bunch of XOR values. So there's this loop, and it's going to be j, we'll say, 0 to it's going to be, I want to say it's I. It's related to I. Yeah, it's related to I. What you're going to say is, basically consider I to be like, the whole game size. In this case, or it's the subgame, right? So consecutive pluses. So if you have like 5 of these consecutive pluses, you have 0 and 5. Now, excuse me, 0 and n minus 2, 5 minus 2. And then you have 1 and n minus 3. And then it goes all the way to, should be like a halfway point where it's basically half of the pluses on the left side, half the pluses on the right side, and then you get the other values. You start to see those next. You see the same values show up again in your set, so you don't need to go all the way across. But I mean, in theory, you could do, basically, it would be this pair. It would be j and I minus 2 minus j. Right. That's pretty much what you're looking at. And then when j is like I over 2, then obviously you get I over 2 and then I over 2 minus 2, and j equals I over 2 plus 1. You get I over 2 plus 1 to I minus I over 2 minus 3. So I over 2 minus 3. Well, actually, this is further. This is past. I think when I say it's I minus 1, you actually end up with. Right, you should end up in this position. I over 2. If I over 2 is even, or I is even, I minus 2 minus 1 on right. This is as far as you need to go, right? After that, it starts repeating. Now this would be swapped with this, right? These two. So we really need to go to I over 2, which would be. If it's even, if I over 2 is even, then would you go to I over 2? If you go to I over 2, you get I over 2 and I over 2 minus 1. Which you don't need to go that far if it's even. If it's odd, then there's sort of like the floor of I over 2. Just thinking How far do you need to go? If it's even, you do need to go to that midpoint, but you don't need to go you don't need to go to I over 2. Just go to I over 2 minus 1. If it's odd, though, then you're still going to get to that spot. Yeah, same spot. It'll just be basically this value won't be quite the same. So this will be like floor of I over 2, and this will be roof of I over 2. So this actually would be the floor of I over 2 minus 1, or just the floor of I over 2, and then this would be the floor, this would be I minus the floor of I over 2 minus 2. I don't think it really matters, actually, realistically. As long as you get enough of it, that's really all you need. You know, it doesn't matter if you include the one off to the side. It shouldn't make a difference, really. Sorry, I'm just doing that. It's a minor optimization. There's some symmetry here, but each of these cases you have dp of j XORed with dp of I minus j minus 2, effectively. And these are the values, state values dot insert, more or less, right? That's pretty much what's going to happen, is that you have all these subgames, this loop of subgames, and each of those subgames be broken up into their pieces, and you take the XOR of those pieces, and dp is basically this function that we're going to be calculating. So you insert into this set these state values, right? And it's kind of it, actually. I think it's that simple. Now the problem that we have is that you need dp of 0. It needs to have some kind of a number. So I think the default was we said give a string that contains these characters. You and your friend take turns to flip. Game ends when a person can no longer make a move. So if you look and you can't make a move, then you lost, right? So that should actually be false or 0 initially, right? Not equal to 0 gives you true, so 0 is false. Okay. What does this do? What does this do if we do this? Oh, really? Yeah, so obviously an unordered set could be very large, very long. Interesting. What's the runtime error? So I is 0. We say j is 0. J is less than 0. Oh. I might have something to do with it. Oh, it worked. Oh, look at that. Oh, that's kind of a problem, isn't it? Because the board set itself, the initial board state, we need to need to get that right. That might be why I was gonna say, I think my code's a lot simpler than theirs. Because you aren't necessarily figuring out the initial board state correctly here. Let's see. So I was saying go through the whole size of the board, but that's not necessarily necessary. What we'd want to do is definitely break this into sub games, and then basically perform this on the largest sub game, right? Sort of set this all out for the largest sub game, and then we can calculate this XOR for the largest sub game of all the games, and do it that way. So yeah, let's just do this first. Break into sub games, or parse into sub games. So the way you would do that would be let's actually just do like an iteration through the string. Let's do it that way. And we'll say character C equals the iterator. And we'll say if C equals plus, then we'll just have a toggle. I don't know, we'll call it T for toggle. False. If this character is a plus, then we toggle equal to true. If toggle is true and the C is equal to either that or is equal to a subtraction symbol, then we'll just have a count as well. So the plus sign, toggle is true, count plus equals 1. And we'll say a not toggle. If toggle, could probably modify this logic as well. Really should set the count to 1. If toggle's off, set the count to 1. So you see this character, keep seeing these characters increase the count. We say if toggle is true and we see a negation, then we set count equal to 0, and we want to vector events. Let's say subgames sizes. Also, I don't think I'm really breaking things into subgames properly, am I? I gotta think about that. I might not be doing this part correctly either. Like I might need to be employing this parsing portion, but I'm not sure if that really is necessary, right? Because you don't actually need to know. Like this is just a calculation on the like if you have the previous values, then this calculation is really straightforward. If you have all the previous values that you need, and you will have them, yeah. So it basically does parse it correctly. So something like that. So yeah, so if it's not toggle it and set the count to 1. If it's already toggled, then we're going to keep going, increment the count. If toggle is true and we see the other character, then we want to set toggle to false. And we want to set count to 0, and we want to take our subgame sizes and push back the count. And otherwise, if toggle is already false, so if not toggle, and this is equal to this, and we don't care about it, we just skip over it altogether. And then finally we say if toggle is still true, and count is non-zero, then we're going to subgame sizes, pushback, count, right? So parse it into initial subgames, and we're going to say largest game is going to be standard minimum of. Now this is kind of interesting. This standard minimum works in a kind of interesting way. I want to say it's a begin and end. It doesn't really use an initializer list. You don't really use a min element. That's what we want. Yeah, that's kind of interesting. Oh, whoops, didn't mean to do that. Didn't mean to click that. We actually want this min element. And that's going to be subgame sizes.begin, subgame sizes.end. Right. And actually it's max element we want, not even min element. And now we want largest game plus 1. Largest game. And then we say take XOR of all of the subgames. So 4, so int ret equals 0, 4, int I equals the subgame sizes, right? Auto game subgame sizes. Ret XOR equals the game. And then we say if return ret not equal to 0. Something like this. And DP is, oh yeah, okay. Something like this. See what happens now. Okay, running, judging, 0 milliseconds. Expected true, 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 true. Interesting. We these are too big. These test cases are too big. Oh, let's try these ones. See how this goes. Whoa. Whoa. Okay. No kidding. Alright, so some of these are not right. How about these ones? How about these ones? I think I know which one's not correct. It's probably this one. That gives us problems. I'll explain why. Yeah, I know why. Let's say, we'll just say this. An if, say, if subgame game sizes is empty, is not empty, then there we go. I think that's why. There we go. Uh-huh. All right. I think we got it. Wrong answer. Wrong. Okay. Don't got it. We don't got it. We don't got it. What went wrong? Diff. Which one is this? 1, 2, 3, 4, 5. 5 from the bottom. 1, 2, 3, 4, 5. What's the fifth one from the bottom? 1, 2, 3, 4, 5. This one. Really? Really? What should this be? I guess if you can't move, then you lose, right? One person can no longer make a move. If you can't move, you lose, right? That's a normal play. That's not misere play. That's normal play. So with a single plus, interesting. Okay. Subgame sizes. All right, we get a 1. So when so we get a subgame of size 1. Well, really, we only care about subgames that are at least size 2, right? So, what we would do is we say if count is less than 2, it's greater than or equal to 2. Right? Only care about. Although, even a subgame of size 1 should be false, right? Like, we could just modify this. So, a subgame of size 1, we would get here, I equals 0. We do all these things. State values should be empty. So it's just really 0. Oh, I see. Well, dp of 0 should just give you 0, no? Or dp of, yeah, no. Size plus 1. Does that give us a 1? dp of 0? Should give us false. Well, oh, that's kind of interesting. It does give us false, but not because we calculated this correctly. It's because this is empty. So there's no game to check. Yeah, so this just goes 0. 0 not equal to 0 is false. But I actually think we should do it this way too. Now dp of 1 is also 0. Yeah. True, false. Oh, so this shouldn't matter, right? Oh, actually, no. Wait, what? That's kind of interesting. Huh. Oh, well, need both. even still. What? What is going on? Wait a minute, what? Oh, because now, no. What? Tarnation. Is DP, yeah, is that, does that work? Can we try that, can we do it this way? I don't know, I'm not sure. Well, this works. This is kind of funny. So, we don't really need to push back. Like, we could push back any subgame size. Like, that should be fine. But what's not fine is the subgame of 0 should be, or of 1 should be 1. Right, by the rules? Or no, it should be 0 rather. Like, subgame of 0 is going to be subgame of size 1 will be calculated as a 1, I think. Right? So we put a game of size 1, subgame of size 1, and we say I equals 0. You say there's no values inserted, so the first missing number is a 1. So DP of 1 of 0 will be set to 1, which is not what we want. So we want I is greater than, it starts off at 2, and we'll say you could do largest game plus 2. I mean, really you would want to do the minimum of these things, right? 2 or the maximum of these two things. Just so we don't run into issues. Wrong answer. Interesting. Output true, expected false. So, oh, this is also, it's DP of game. I don't know, how did I get all the other ones correct? Yeah. Why did I... What? I'm just really confused. How does everything correct if I wasn't doing this properly? This is not right at all. Which one's wrong? This one? 1, 2, 3, 4, 5. Fifth one. Okay. 1, 2, 3, 4, 5. This one is wrong. Alright. Awesome. Of course. Of course. True, false. What? No. Come on. Yeah. 1, 2, 3. How many is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So we got 15. So we ret DP of 15. And it's just wrong. It's just false. Nope. Well, I mean, really? Really? Huh. You could do this too. Could try that. Um. Oh, maybe not. Maybe not. Maybe this goes off in the wrong direction. Like if I is 2, then you get 1, J is 1, I is 2, J is 1. Oh yeah, never mind. That's wrong. That'll give you 2 minus 1 is 1 minus 2 is, yeah, it's too far. However, what now I'm just confused. I am just confused. dp of 0, there's no states to go to. dp of 1, there's no states to go to. dp of 2, there's 1 state to go to. Zero, 0, and 0 gives you first missing number is a 1. Return not equal to 0 should be a false. Alright, how do we reconcile these things, man? Oh, we got a long ways to go. Got a ways to go. Let's just try that. Try that for now. There's only one at the bottom that shows incorrect. Now I have this funny feeling that has some more to do with the fact that they didn't calculate that many test cases that far ahead. I got this feeling. That it has something more to do with something that was not necessarily my fault. Not necessarily my fault. It's exactly the one at the, everything else is right except for the one at the bottom. Now why would that be? Why would that be? And it says the wrong answer, so apparently we should be able to calculate this one. Now, a few questions. Why? Why is it that this one is fine, but this one's not fine? How does that happen? How does that happen? Excuse me. You don't really need this, by the way. If we set this back to 0, do we get the right values? The first one and the last one. Set that to a 1. A lot of these give us true. Is this just always true? Didn't notice that. No. Yeah, they're all true. Wait, what's going on here? There's a few of these that are wrong. How did I miss those? What? This is kind of funny, huh? Wait a second. What's going on here? What is going on here? What is this? Let's just take a moment to add that back. I don't think it works even if you have that. Oh, it just gives you true for everything. That's not correct. Why is that? Now, why is that? Uh-oh. Uh-oh. Alright. So I think the algorithm itself is wrong. I think it's got nothing to do with whether or not interesting. Okay. So yeah. Very interesting. Before I just did DP, of the game itself, I XOR'd the game itself. All true, huh? It should be the game, DP of game. Now, I don't really understand, Struggling to understand. There are some of these things that are false. So here, where's the example? It's false, right? 1, 2, 3, 4, 5. Fifth one should be false. Okay. 1, 2, 3, 4, 5. All right, this is the one I want to focus on. These two, or just this one. Man, this is interesting. So it looks like everything comes out true, which is not supposed to be the case, right? It's not supposed to. You're not supposed to have that. We're supposed to have this recursive function. Right, obviously, the largest game. We don't need everything. DP, we have less than or equal to the largest game. So we would say rets 0, XOR that with take every game sizes, and for each game, subgame, right, you XOR with. So this makes sense. I mean, this is fine. Now the thing that's not fine is what is going on over here? This is just always true. Like this always gives you true, which doesn't make a lot of sense. Because this could be 0, right? Now, I guess the thing that's weird to me is this first missing number always gives you a positive number, right? It always gives you a 0 or 1. So that, I guess that's what I'm stuck on, is why would the smallest positive number that is not set y? I want to say it includes 0. I think he misspoke when he said smallest positive. I think he meant it could be 0, starting from 0. So you'd say 0 less than the size, and then you return the size. I think that's quite possibly quite possibly what was meant. Yeah. Impossible. There we go. Yeah, that's what it was supposed to be. Okay, I was gonna say, I was like, I don't think this algorithm makes sense, given that if you can only ever get positive values out of there. It's getting a little frustrated there because I was like, man, going through all these test cases and whatnot, and doing all this stuff. It's not working. It's because it's not the smallest positive value, it's the smallest non-negative value, which is different from positive. Yeah, non-negative is not the same as positive. All right, let's go for it. Hey, 100%. Sweet. And not too much memory. Nice. Got 0 milliseconds DP. How you like them apples? How you like that? How you like that? Hey, although I think he was saying he also got it down to like 0 milliseconds. Yeah. Okay. Same. Dude. Yeah. So I guess right. I was gonna say. I was like, I don't think you can just take only positive values for your results, right? Because then everything, it would just always return true. It's exactly what happened. So it's got to be 0. 0 is the losing state. Yeah. So really, you would be 0 or 1. I think you could have 0, 1, or 2. Like I want to try that if we can do. Let's just do a test, right? Let's say if dp of I is greater than 1, standard test, right? If we do this, yeah. Okay. So we do need to use integer. I wanted to try to save some space by using Boolean values in the what do you call it? Save some space and use Boolean values for the DP rather than integers. Thought that was the Booleans and integers. If you used because this find missing number uses integers, right? But technically, if there's only 0 or 1, then you can do. But if you have 0 and 1, then obviously you have another state entirely, right? You have, yeah, pretty neat. So you really don't need. Yeah, it's kind of arbitrary then. So now you do kind of need integers then. I wanted to test this to see if we could possibly represent this with only 0s and 1s, but I don't think you can. I think you need to use it. Yeah, you get a whole bunch. You do need to use you do need to use the other thing, which is integers. You need to use more than just Booleans. So it's kind of neat. Really interesting solution. I mean, this is basically the whole code for. This is the whole DP right here. Super succinct, like really awesome. Like I'm really glad that we got to look at that. You know, that person took the time to add some game theory. Really neat. So this is. You know, it's funny too because I was thinking about it. I was like, I'm pretty sure that there's a way to do this. It's a lot faster than backtracking. Said that initially. I was like, yeah, with games, like especially if they're certain kinds of games, well, impartial games in particular, you can optimize the speed quite a bit, I believe. Yeah, impartial games, which would be, this is an impartial game, or potentially can optimize, right? If you can break it down into sub games relatively easily. It depends on the game. It's impartial, normal, and then also has impartial, normal, and then also has the ability to relatively easily break it into sub games, based on each move. Then in those cases, it's relatively straightforward to calculate. It can be relatively straightforward to calculate the solutions. Really neat, really interesting. So yeah, you can use this Sprague-Grundy function. what an amazing thing, right? Like, so game theory is super interesting. I don't know anything about it, but definitely really neat. Really neat. Couple of theorems from game theory, right? If you define your Sprague-Grundy function, define a first missing number function, then you have a theorem, couple theorems. If the Sprague-Grundy function is not equal to 0, then the first player can guarantee a win from the board state. Otherwise, no matter where the first player moves, the second player has a winning move. And then the second Sprague-Grundy theorem is that if you can break the game into sub-games, then from that game state, then you can calculate the same function with XORed on the game states. Pretty wild, pretty amazing. Yeah, there you go. Calculate G of 0 to max of S of I using DP. And then if they're all, XOR them all and they're not 0, turn true. Super succinct, super simple. Takes quadratic time. I think what he wrote is actually more concise than what I wrote. Length of all continuous. Get the maximum at the same time. Oh, I didn't think to do that. Oh yeah, we actually can do that in tandem, simultaneously. It's a good thing I read his code also. Yeah, just do larger scale. Yeah, you don't need this here. You could just do and should work the same. Alrighty. A little more concise. What routine did he use to parse? And what routine did he do to do the XOR? I mean, this is pretty good too, but Totally unrelated to anything we're doing right now. It reminded me of in my life, I've dealt with alcoholics quite a bit, and what I've learned is that there's this inability to accept reality for what it is. And that seems to be what really nails alcoholics. And also, I think the same thing for drug addicts, and I think the same thing for addicts in general. Like, I'm pretty much an addict in my life, how I've lived it, and how I sort of continue to live it. I kind of suffer in certain ways because of that. And addicts have a hard time accepting reality for what it is. And in particular, it's self-pity. That's what it is. It's feeling sorry for themselves, feeling bad for themselves. Addicts, I believe, I could be wrong, but I believe they basically indulge in self-pity. Their view of themselves is very negative. They indulge in self-pity, and because of that, they pity themselves. They're extremely selfish, right? Because the thing with drug addiction and any addiction really, it's extremely selfish. You're totally focused on yourself, right? And the reason you're so focused on yourself is because you pity yourself, right? In other words, you were abused, you were mistreated, you were treated unfairly, all of those things. And instead of accepting that that's normal to be abused and mistreated, which it is, by the way, but from other people, even people you trust, people you love, that's totally normal. And I explain what I mean by I don't mean it's okay. It's not okay. It's not good. It's not good. It's not okay. It shouldn't continue, all of that. But I mean, it's totally normal in that the Bible says pretty clearly about what the heart is evil continuously. So you're just constantly evil. And the people you deal with, everybody you deal with, is constantly evil. And they're going to treat you unfairly, they're going to cause you to suffer, they're going to do all kinds of nasty things to you, all kinds of nasty things. And I think for really young people, when they're mistreated really, really severely, when they're very young, it's extremely difficult when they grow up for them to sort of not pity themselves as they go. And they become addicts, right? That's like the big thing. When you pity yourself, you don't focus on anything other than yourself because you need attention. You know you need attention. You pity yourself. You know you're not good enough. You know there's something wrong with you. You know there's something about you that's broken and you can't fix it or something like that. About how you were treated. You basically internalize how you were treated and pity yourself permanently. You think that you're somehow less than because of that. Because I'm going through my own thoughts because I'm an addict too. That's the thing. It's like I see these other addicts, these crack addicts and these heroin addicts. I've dealt with addicts in my life, and I've also in a way where I sort of was a third party to see their misery and what they've been doing themselves and all of that and the situations they get themselves into. Alcoholics and heroin addicts and things. And I've also been watching this guy recently who was talking about, he does interviews with these people. He goes to Skid Row, and I've been watching a lot of that. Well, for a few different reasons, but I've been watching that, and what's interesting about all of that is you might find a guy who's addicted to crack, who's sort of high functioning, doesn't lose his job, but he's still addicted to crack, and he's been doing that since he was 25. He's 42, right? 17 years. 17 years later, he hasn't figured out what to do, what the problem is, how to stop. And I have the same problem. I mean, I'm not a crack addict, but I have the same issue where I have certain addictions that I can't figure out what to do about them, how to fix them, how to change them, how to be like normal, how to be human, right? And I realize it's self-pity, always. It's self-pity. That's what causes the problems. It's what causes me to run into more problems. It's just this kind of cycle of pity. You feel bad for yourself. You feel sorry for yourself. So then you basically degrade yourself and then you run into more problems, and you use that to justify, oh, okay, I don't deserve, whatever thing it might be, because clearly I'm so, I guess, weak and not good enough and all of that. And you heap on that self-pity. It just struck me, because I'm like, I think, just think about my thoughts. I've been thinking a lot lately, and I've also been kind of thinking about my thoughts as I'm thinking them. And it's pretty rough, man. It's like my mind goes to some pretty dark places really quickly. And it's funny because like I pretty much haven't left my room. Like the only time I leave my room is maybe go to the gym, maybe go get food, and maybe supplies, like paper towels, things like that, whatever, at the local superstore. That's it. I don't even leave. I don't do anything beyond that. Obviously I spend a ton of time, I basically spend all my time in my head and on the computer, right? Communicating with other people in different ways. But that's it. That's my whole life. That's it. I'm just totally, I don't even move, which is amazing. But, I'm just totally in my head at all times. And it's not as cozy in there as it could be or should be. Like I solve all these problems and that gives me some respite. Really any addiction, for me, the whole thing is like I just need to feed the addictions that I have so that way I could forget about who I am, something like that. Forget my existence. That's kind of like the goal of my life, is just to forget who I am. I've been thinking about that. It's like, well, isn't that suicidal? It's like, yeah, that's exactly what I've been thinking about lately. It's like, oh, right. I guess the first thing is we'll stop doing that. Stop that. But yeah, it's like, oh, you're actually literally trying to kill yourself. That's your behavior. That's what you're doing. It's like that. That would make sense, wouldn't it? That a person that pities themselves is basically slowly killing themselves. That's what addicts do. That's what they do. They basically pass the time until they're dead. Like they're looking to die. They don't have any way out of the horror of their own psyche, other than to get hardcore addicted to something that'll just wipe away all those memories. Never even knew what happened when you were younger. What happened, how you were treated. Like I said, pretty dark, pretty quick. But I wasn't gonna get into all that. But I realized that, like, yeah, it's actually the purpose of addiction is actually to commit suicide. Basically, you consider yourself unworthy of life. So you try to do everything you can to forget it, forget you exist. It's pretty rough, man. That's pretty brutal. It's pretty rough. But anyway. So I wrote the same routine. Interesting. So the way that he wrote that routine is slightly different from what I did. I used a toggle, but you don't need to use a toggle. You could say count, and you just say if C, then you plus plus count, and then you say if. Did something interesting towards the end here. If you're here, then set count to 0, largest game, push back to game. But the thing that he did that was interesting to me over here is this part. I plus 1 is the size. So right at the end, you also see either the character or you're at the end. I didn't think to do that. I plus 1 is equal to, or it plus 1, s dot end. There you go. You don't have to do this extra part at the end, right? I don't think so. I'm sorry, what? Actually, you just do if. These are sort of mutually exclusive, somewhat. Doesn't really change the speed very much, but it changes the elegance of the code, if that makes sense. Oh, also that too. It's more elegant, more easier to read, easier to write, right? The reason why you want to put this if outside of this one and not an else if is because you want this to happen regardless of what happens here. You have to remember that for well, I guess yeah, it's good. It's good to just watch, take a look at someone else's routine, see how they wrote it. Obviously, we did this fine. This is much better now that we took a look at how how other people handle parsing like that. Yeah, this is exactly the way he did it. He put something a little bit different here, so this part was a little more clear. This is the first game, second game, and then the XOR used. Obviously, when I use integers, when I loop through integers, excuse me, a reference is an integer. So I usually don't use this reference here because I figure it's like, well, you're not really saving much more space, are you? However, actually, if you're dealing with different sized integers, I think it's better to just always use an auto reference, because if you're using different sized integers, then there's some potential for like speed ups, I guess, like different width integers. Wow, how many times I hit that submit button? Yeah, this is cool, man. This is really interesting way to do it. I definitely wouldn't have thought of this. I mean, there's no way. Basically, now the thing to do would be to go and learn what is a little bit about game theory now. This these two theorems. It's impartial normal play. You get Sprague-Grundy function, which is basically you have a scorecard for your. You have to have some kind of a scorecard for your states, your sort of base states, and then you write, you get, and then the function is going to be the first missing number, moving from one board state. For G of that board state is going to be the first missing number of all of the board states of all of the possible moves, and then right, first missing number is the smallest non-negative number, not positive, non-negative number, and then that's not in the set. And then you also have another theorem of the Sprague-Grundy function is if you can break the game into subgames, then this function can be calculated as the XOR of each subgame of this function applied to each subgame, which is extremely useful, right? Because you can start really reducing how the difficulty of calculating this. And then from there, if your game itself lends itself to a relatively straightforward sort of, let's say, set of subgames, or each move kind of breaks the state, and it breaks if your game is such that moves break the board state into subgames relatively easily, then you're in a really good spot, because now you can basically calculate the XOR of those subgames to give you the function, or you can generate that set of values from those moves and those subgames that are produced. Yeah, pretty interesting. If you can more or less define your board state as subgames, a sequence of subgames, then you're in a really good spot. And if your moves just take you from one set of subgames to another, that's really good. It's super easy. Super easy. Or it's easier, I guess. Really neat. Wow, this is amazing, man. I don't know. I'm like floored by this. This is pretty unbelievable. Pretty unbelievable. All right, that first theorem that you win. The first player wins if and only if the first player is guaranteed a winning move from board state X if and only if this function is not equal to 0. Otherwise, the other player has a winning move. Otherwise, the other player is guaranteed a winning move. So I guess there are like some things about this that, basically, I guess what it means is that your game is decidable, something like that, or you can guarantee that a certain player is going to win or not win from any board state. I guess that's kind of like baked into all this theory of game theory, is that there are some games where there's a name for that. Not decidable, or notably a decidable game. What is that? Decidability is not the same thing. No-win situation. Yeah, it's decision problems. It's not the same thing as games. Level does not end once a player fails an objective short of being killed, but it is impossible to progress to the next level no matter what the player does afterwards. Nice. Nice. Interesting. Film war games simulates all possible games of tic-tac-toe as a metaphor for all possible scenarios of a nuclear war, each of them ending in a nuclear holocaust. Computer then exclaims, "A strange game. The only winning move is not to play." It's dark. It's dark. We're looking for infinitely long games, discrete continuous games, differential games, evolutionary game theory, stochastic outcomes, relation to other fields, metagames, pooling games, mean field game theory, representation of games, prize-winning achievements in games. Doesn't everybody love games? Who doesn't love games? Game. I'm looking for all the way in here. General and applied uses retail and consumer product pricing, economics and business, the business. We're talking about the business. Nash equilibriums, right? Subgame, perfect equilibria, solution concept. Trembling hand, perfection. Refinement of Nash equilibrium. Interesting. Trembling hand, perfect equilibrium. Whoa. I'm looking for common knowledge. Common knowledge is a common sense. Must have a common sense. Evolutionary game theory. I'm looking for something specific. Perfect information. Know the moves previously made by all players. Most games studied in game theory are imperfect information games. Examples of perfect information games include tic-tac-toe, checkers, infinite chess, and go. Infinite chess. Please no. You just send your queen off into take all your pieces and put them in infinity and just where did those pieces come from? Even though it's infinite, you can still have perfect information. That's fun. Complete information. It's not the same thing. Not the same thing though, right? Every player knows the strategies and payoffs available to the other players, but not necessarily the actions taken. Incomplete information can be reduced. It's fun, but I'm not really interested in all that. I'm really more interested in how do you players move simultaneously. That's fun. What I'm looking for is it's not these things. I'm looking for I don't know if I could do this. Do it this way. I can't find it. Game theory is wild though, man. That's some pretty interesting stuff. It's pretty interesting stuff. I'm looking for oh, that's crazy. Normal play nim, or more precisely, the system of nimbers. The Nimbers. Shiver me Nimber. Okay, I'm sorry. Something about that, it's really funny. Yeah. Fundamental to Sprague-Grundy theorem. Oh, no kidding. That's where the Sprague-Grundy came from. Ah, it's related to that. Essentially says that in normal play, every impartial game is equivalent to a nim heap that yields the same outcome when played in parallel. Other normal play impartial games. See disjunctive sum. Whoa. Ah, that's okay. Well, that's what I'm looking for. The Nimitron. 1940s Nimitron. That's awesome. That's a lot of fun. But no, I'm looking for something specific. Winning positions, math theory, proof of the winning formula. I'm looking for something very specific. When you know who's going to win the game, all players play perfectly, and you know who's going to win the game. There's a definition of a word that I'm looking for. I thought I would find it here. Solved. A solved game. Okay. Outcome, win, lose, or draw can be correctly predicted from any position, assuming that both. Okay, there we go. It's a solved game. All right. Yeah. Took me forever to figure that out. But what I wanted to say is that we're assuming this is a solved game. Given that this is a solved game, we can apply Sprague-Grundy function to actually figure out who solved it, or figure out who wins. All right. Oh. Brother. That's what I was trying to do. Just try to figure that. Just find that one word. It's one description. One descriptive word. Solved. It's a solved game. Yeah. So, a normal impartial game can have an analog. In many cases, has an analog to nim, and because of that, you can actually state that it's a solved game, and then depending on the game, you may even have enough computational power to solve it. Solve the game. So that's what all that's about. Interesting though that the Sprague-Grundy theorem basically is highly related to nim, because I was like, oh, nim's great, it's an interesting game, but it's really pretty interesting, specifically important game with regard to game theory because of how it's related to the Sprague-Grundy theorem and some theory about impartial games. Now, a lot of the games that people play today, very different. The really popular games, right? The video games that people play today. It's a whole different ball game. But anyway, all right. Let me get on with it here. Obviously, really interesting. Got to tinker with some game theory. Obviously, I alluded to a nim problem that I'd solved way back when. That nim problem would be solved with Sprague-Grundy theorem. Yeah, so pretty nifty. All right, let's go ahead and we're going to end the stream there and say thank you for watching. I appreciate it. Talk to you soon. End the stream, take a break for some period of time, pick up another problem. That's the plan. So thank you again for watching. I appreciate it.